warm-up, and we were given a circuit where you know the voltage and you know the resistance, and you had to find the current. Now, you might remember from the previous class that we solved this using some sort of magic triangle, and we can draw one such as this. Yay. Here's our triangle. Right. We get V up here, I times R below, and so we can solve Ohm's law, right? This is just Ohm's law, V equals IR. But it's arranged so that we can quickly figure out if we're looking for current, right, which is I, we can just cross this out. We get V over R, and we say V over R equals 18 volts over 3,600 ohms, and that happens to be equal to 0.005 amps, right? Why do I know that? Because we solved it on Friday. Otherwise, I would have to punch it into a calculator, and we would do something like this, and we'd say 18 divided by 3,600, 3,600 equals, right, 0.005 amps. Okay, so we could do that. We started taking notes on resistors, and we said there are two kinds of circuits, and we said there are two kinds of circuits that we're going to study, series and parallel. And what I wanted you to notice is that if we start from the positive part of the battery, we know a circuit goes all the way to the negative part of the battery. Well, if we do that, if we follow this circuit through that, every bit of current that goes through this first bulb has to then go through the second bulb. So all of the current from one has to go through two also before it can come around to the negative end of the battery, right? And so the first thing we said was that in this one, current, right, current is constant. And that's going to be a really important thing for us. It's going to help us solve a lot of problems. So the current in a series circuit is constant, and it's because there's only one loop, and it means that all of the current going through both bulbs has to be the same, or through all parts of the series circuit has to be the same. So there's only one current in series. The other thing about it is that as the current gets slowed down by resistor 1, it then goes to resistor 2 and gets slowed down again. So the resistance adds up. In other words, that since every bit of current sees both resistors, the resistance of the system is the sum of the two resistors, right? And we'll see that again in just a moment. If we have a parallel system, then as we go through it, we get to a point where we have a choice, right? All of a sudden we have this junction where it can go one way or the other, right? And the current that goes through bulb 1 can come around and get back to the battery, right? Go from minus to plus. And so here's one loop, right? But if we follow this other thing, right, we can go through bulb 2, right, and come back to the battery again. And so I can think of this as being a whole second loop, right? So there are two loops in this case, each with their own current. And they're not necessarily going to be equal. It would depend on the resistance. So the current actually splits. So current is definitely not constant. However, what you can notice is that if this is connected to the positive part, if the positive part of the battery is up here, right? If this is positive 9, say, positive 9, this represents like 0 volts, right? If this is 0 volts and this is positive 9 volts, right? Then this part of the bulb has to be 9 also, and this part has to be 0, because this is connected to the bottom of the battery and this is connected to the top. Similarly, this has to be 9 and this has to be 0, right? You can see that the gap across the battery, the voltage change across the battery, has to be the same voltage change across each of the bulbs. And so we see in a parallel circuit, the voltage is constant. And that's going to be really handy for solving problems. So voltage is constant. So if you have a series circuit, the current throughout the circuit is going to be your constant, but in a parallel circuit, the voltage is, okay? And so that's basically how we're going to solve these things. Let's take a look at this kind of quickly. Mathematically, we have two resistors here, 20 ohms and 10 ohms. So the total resistance should be the sum because all of the current goes through both. And so we're going to say that the resistance is 30 ohms, right? 10 plus 20. However, if we plug this in on the simulator, we see that we had 9 volts. When we measure the current, we get 0.3 amps. And so the total current and the total voltage give us, using Ohm's law, right, our magic triangle, right? If we're looking for resistance, V over I times R, right? If we're looking for total resistance, we cover this up. We get V over I equals 9 over 0.3. And when we divide 9 over 0.3, we get 30. And so we have 30 ohms by adding the resistors, or by dividing total voltage by total current. You can see that it works out the same way. Another thing we get from this is that the total voltage drop in this case is going to be the same as the battery. Right? When we measure the current, it's 0.3. When we measure the voltage drop across this resistor, it's 20 ohms. Well, that makes sense because 0.3 amps times 20 ohms gives us 6 volts. I should have put amps in here, right? Times 20 ohms gives us 6 volts. And so that's the voltage drop across the 20 ohm resistor. Same thing with 10, except that now it's 0.3 amps times 10 ohms, so I get 3 volts. Well, that makes sense because this is using half the energy, right? This is using twice the energy, right? In other words, that as the current passes over the 20 and the 10 ohm resistor, 2/3 of the energy is being consumed by the 20 ohm resistor. Only 1/3 of it is being consumed by the 10 ohm resistor. And so we get 6 volts and 3 volts. And so when we add them up, the two bulbs add up to the light bulb, which makes sense because that takes us back to the negative end of the battery. So we get our 6 volt drop here, our 3 volt drop here, and then we're back to the beginning, to the 0 volts that we started with. All right. Now in a parallel circuit, it's a little different, right? We said that the voltage is going to be the same, right? The voltage is going to be 9 volts no matter what. And if you look at the currents, we have more current where we have less resistance. Now that actually makes sense. If we have like a highway, like if you think of it, if you have Randolph Road is just like 2 lanes in each way, right? So if you have Randolph Road with 2 lanes going in each way, and you have the Washington Beltway with 5 lanes going each way, you have a lot more cars taking the Beltway to go east-west than they do than Randolph Road has. So with more resistance, a slower road, Randolph Road, has fewer cars. With less resistance, a bigger road, the Beltway has more cars, right? And so there has we can see practically that as resistance goes down, current will go up and vice versa, right? But the other thing you can see from this is that we get the same voltage, right? Smaller resistance, bigger current, same voltage, right? The voltage is constant. Okay. Right. Another thing we can get from this is that since the resistance goes down when the current goes up, and since the current adds up, in other words, if I had the total current here, I total, right? And then it splits up, right? I1 and I2, right? I1 and I2 add up to the total resistance. Well, I1 is just V over R1. I2 is just V over R2. When I add them up, I get V over R total. But you can see that resistance is always in the denominator. R is in the denominator. Right? So for parallel systems, right, resistance is in the denominator. And so instead of getting R plus R equals R total, we're getting 1 over R1 plus 1 over R2 is equal to 1 over R total. That makes it a little awkward to punch it into a calculator, right? We're going to get 1 over 10 ohms in this case plus 1 over 20 ohms, right? And I'm going to have to punch it in and start adding it up, right? So if I look at my calculator here, I'll say, if I clear it, right, I'll say 10, and I'll use the inverse button, right? plus 20, and I'll use the inverse button again, equals, right? And I get 0.15, but that's not actually my answer. 0.15 is still 1 over the answer, right? So what I have to do is remember that the total resistance is 1 over that thing I just got. And so all I have to do is hit this, and there's my answer, 6.67. Okay? So you can solve it on a regular calculator, but you have to be careful, because when you're done doing your addition, you're getting 1 over the total resistance, not the total resistance itself. All right. By the way, if we actually took that 6.67 and put it and force the resistor to be 6.67, I could use a single bulb, and I call this the equivalent resistance to my parallel system. Right? When I put that into the simulator, you can see 6.7, that's the closest I can get to 6.6666 repeating, gives me 1.34 amps, right? My 10 and 20 together gave me 1.35 amps. So you can see that this is basically the equivalent resistance, right? The equivalent resistance to 10 ohms and 20 ohms in parallel. So that was the notes that we did, and then we wanted to practice it. So what we did was we went here to Cami, and we did some problems. Now this problem sheet is available in the module, but it was also available to on paper in class. So if you look at this problem, we have this problem laid out, and this is going to be a series circuit, okay? Now I've drawn it out, right? 110 volts, 33 ohms, and 22 ohms. The first step I want to do is I want to write what I know in the problem. So under resistance, I'm going to put 33 ohms, right, and 22 ohms. Under voltage, I'll put 110. But this is the battery voltage, so it's like the total voltage, right? I know that these are going to be smaller drops, so I'm going to put 110 here. But there's another thing I want to point out. I also know that the current is going to be constant, and so I'm going to write this down so that I remember that the current is constant because it's a series circuit. Okay? So that's everything I know at the beginning of the problem. What I need to do now is figure out some missing piece. I'm going to start with the total resistance. And the total resistance I know because the series circuit is the one that just works intuitively. Yeah, the total resistance is the sum of the individual resistors, and we see that up here in the equation, right? I can just add up R1 plus R2 and get R total. So if I do that here, R1 plus R2 gives us 22 plus 33, which is 55 ohms. Okay, so 55 ohms. Well, now I have 2 out of 3 things in this column, and I can just use Ohm's law. So if I take my magic triangle, right, and I put V over I times R, in this case, I'm looking for I, so it's going to be V over R, just like in the warm-up. And so this will be V over R, which will equal 110 volts over 55 ohms. And you don't have to be a great mathematician to realize that 110 divided by 55 is just 2 amps, right? But if you didn't recognize it, you would haul out ye old calculator, and you would say, hey, calculator, what's 110 divided by 55? And it would say to you, nothing. You have to look at me. No, it would say 2 amps, right? So there we are, so 2 amps. But remember, it's constant. So we got 1 answer, but we really got 3 answers because it rules. So now we have 3. So we got 2 amps, 2 amps, and 2 amps. At this point, we now have 2 out of 3 in every column. So we can go back to our magic triangle, right? V over I times R. Well, this time we're looking for V, so it's just I times R. So we're just saying 2 times 33, which is 66 volts, or 2 times 22, which is 44 volts. And you can see that the 66 volts and the 44 volts add up to 110, right? And so that's our total voltage. So series works out pretty well. It's pretty straightforward. Now, we're going to go ahead and solve a parallel system next, just because I want to break it up. I don't want to just do the same thing over and over. So if we look at a parallel system, we're going to play the what do you know game again, that's the system always. You want to first write down the stuff that you know so you can organize things and actually figure it out. So I have the resistance, so I'll write those in under resistance, right? Because those are already given to me. I might as well write them in. However, I don't know the total resistance because this time I have to add the inverses if I'm going to do the total, okay? And we'll come back to that. I also know the total voltage, 12 volts. But there's one other thing. I know that in this one, the voltage is constant. And so if the voltage is constant, then I can simply put 12 volts all the way across because they're all parallel. Okay? So 12 volts, 12 volts, 12 volts. Well, there are two ways of attacking this, but the way I'm going to start, just because we need practice, is I'm going to start by finding the total resistance. Well, I know that that's the sum of the inverses will give me the inverse of the total resistance. So I'll say 1 over 120 plus 1 over 60 plus 1 over 40 will equal 1 over R total. Right? So I'll go to my calculator and I'll say 120 and 1 over plus 60, and I'll go to the 1 over button plus 40, and I go to the 1 over button, and that's everything. It's 0.05. So I can go over here and say 1 over RT equals 0.05. Well, if that's true, right, then RT equals 1 over 0.05. So when I do that, I'll go to the calculator and just take the inverse of that, and it'll give me 20. Okay, so let's see what we get. So this should be 20 ohms. Okay. So now I can find the current in any one of these branches using V equals IR, right? If I'm looking for the current, if you'll recall, when I do that whole magic triangle thing, V over I times R. If I cross out the I get V over R. So I'm going to just take 12 over 120. Well, in this case, 12 over 120 is simply equal to 0.1, right? Because it's 1/10 basically, right? And 12 over 60 is going to be, when I punched it into the calculator, is going to be, I believe, 0.2. And these are amps, by the way, amps and amps. And then 12 over 40, I don't know off the top of my head, but I can punch it in. 12 divided by 40, and I get 0.3. And so I can get 12 over 20, right? I'm pretty confident that 12 over 20 is going to be, well, let's actually just figure it out. I don't have to be confident. 12 divided by 20. And that's 0.6. Okay? But actually, I knew that anyway because the total current in this system is going to be the sum of the currents in the branches. So 0.1 plus 0.2 plus 0.3 is also 0.6 amps. So the total current is going to be 0.6 amps, and I can get it by Ohm's law, or I can get it by adding up the little currents. Okay, so 0.6 amps. Well, let's go back and do another series one, and let's see what we got. So on this one, we've just got more resistors in series, right? So if I were to draw this out on a schematic, I'd have 120 volts as a battery, and a battery is just this little double line system where you have a short line for the bottom of the battery and a long line for the top. And then it goes to 4 resistors, and resistors are just little zigzag things. So little squiggly zigzags represent each resistor, and you just put them in a row because we have a series system. And so I label them 4 ohms, 8 ohms, right? And I can label them with all that, 12 ohms and so forth. So I see I have the same thing with just more resistors, okay? And so I'm going to label, and this is what, 120 volts, 120 volts. So here's my 120 volts, and I'll write in my resistances. right? And I remember further that the total resistance is just the sum. So I can just add 4 plus 8 plus 12 plus 16. So 4 plus 8 plus 12 plus 16. And 4 plus 8 is 12. 12 and 12 is 24. 24 and 16 is 40. Okay? So 40 ohms. That's my total resistance. My current, I know, is constant, by the way. I should have written that in. Okay? And I can figure out the current from Ohm's law. If you'll recall, this is just going to be V over R. And so I can take 120 over 40, and I can find that 120 over 40 is 3 amps, right? And so I'm going to get 3 amps all the way down. 3 amps, 3 amps, 3 amps, 3 amps. And so most of my problem is already solved. Yay. And then I can remember that for this row, volts, right, V equals I times R. And so I can simply multiply 4 times 3, right, or I times R, 3 times 4, it's the same, gives me 12 volts. 3 times 8 would give me 24 volts. 3 times 12 would give me 36 volts. And 3 times 16 would give me 48 volts. So when you look at this, right, it's the same process as before, we just have slightly more resistors. And so we add them up to get the total resistance, calculate the current. The current is the same all the way through, and we can simply multiply I times R to get any voltage that we care about. Okay. So last but not least, we did the second parallel system. And again, with this parallel system, we now have three resistors. The only difference between this and the first one is the numbers are different. And so we are going to do the same thing. We're going to write down what we know: 10 ohms, 20 ohms, 30 ohms, and the total voltage is 120 volts. But as we said, this is constant. And so we can simply write it in all the way across. Now, there are 2 ways of getting this. I said there were 2 ways of getting to this answer, the total resistance before. You might notice that we have 2 out of 3 things in every column here. That means if I wanted to, I can simply calculate the current. I know that current is just V over R, right, from our whole triangle-y thing, right? Here is V over I times R. And so if I'm looking for I get V over R. And so 120 divided by 10, right, 120 over 10 is simply 12, right, 12 amps, right? 120 divided by 20 is just 6 amps. 120 divided by 30 is just 4 amps. And so now I can actually get the current by simply adding them up. 12 plus 6 plus 4 is 22 amps. So I'm pretty sure that this is going to be 22 amps. Okay. Well, I don't know what 120 divided by 22 is, but I'm pretty confident it's going to be the total resistance. So let's check this. We're going to check this 2 ways. We're going to solve for the total resistance just like we did above. And then we'll actually solve for the total resistance by dividing volts times amps. Volts divided by amps, right? So let's try this. We're going to do total resistance is 1 over 10 plus 1 over 20 plus 1 over 30 equals 1 over our total. And if I do that, I go over here and I say 10, 1 over, plus 20, 1 over, plus 30, 1 over, and I get 0.183. So if I go back here, 1 over RT equals 0.183, and so RT would equal 1 over 0.183, and that we can find quickly by just hitting 1 over and equals, or actually we don't even have to hit equals, is 5.45 ohms. So 5.45 ohms. All right. Well, that means we can get that here. 5.45. Oops. 5.45. Now we can actually check that. We can say, take the 120 over 22 and see what we get. So if we have 120 divided by 22, hey look, there's our 5.45 again, right? Or we could say, okay, well I know that this works. I could take 120 over 5.45 and I would find I still get the same total current of 22 amps. Right, so there are really two ways of going about this. I can solve by this by summing these things up, or I can solve for the current by simply calculating the total resistance and dividing it into the voltage. Okay. Now we're going to do the other two problems when we get back to school on Tuesday, or you could practice them on your own and come to school ahead of the game. On Tuesday, we're going to finish this and work on power and how this connects to wiring things in your house. And then on Wednesday, or if you're on the block schedule Thursday, we will have a quiz on electricity and we will catch up any missing papers. Okay, so we'll be looking for anything that needs to be turned in then. Okay. And that should take care of that.